Alright, so titration is the slow addition of a solution of known concentration, called a titrant, to a known volume of another solution of unknown concentration until the reaction reaches neutralization, which is often indicated by color change. Basically, it's a method for determining the concentration of an unknown sample. Some chemicals decompose over time, break apart. If you were to pour Coke into a pan and leave it out for a while, eventually the water will evaporate and the Coke will become like syrup and get more concentrated. So over time, chemicals change concentration. And often you need to re-measure how concentrated your stockpile is. So here's a problem. In a titration, 27.4 milliliters of a 0.0154 molar solution of barium hydroxide is needed to neutralize 20 milliliters of hydrochloric acid. What was the concentration of the acid solution? What does it mean to neutralize? Get rid of it. So completely destroy all the HCl. Ooh, no. Ooh, no. Where should we start with? What's the first thing you would imagine we should start doing? And there's a few places you could start. I would personally start with figuring out what the reaction is. So we're taking barium hydroxide and we are reacting it with HCl. What does that make?
You would put the H and then
You don't need brackets, but H2O. H and OH make water. That's a very common reaction. H plus ions plus OH ions give you H2O. This is double displacement, so what will be the other one? Is that right? What's wrong with it?
on the right side there's 3 hydrogens.
There's a bigger mistake. This is wrong. What is it? What happens when barium and chlorine mix together? What do they make? So what's this ion? What ion is barium? So we know OH is OH negative. What must barium be? Are you sure?
No, it should be plus
2 plus, because there's 2 of these. And what is chlorine? Chlorine is Cl negative. So what is the answer? Yes, there should be a 2 on there. Now we balance. What is the correct? So we have 2 oxygens, 2 hydrogens. We also have a hydrogen here. So where do you want to start with? So
you put a 2 on HCl and put another 2 on H2O.
does that make it balanced? That would make it balanced. 1 barium, 2 oxygen, 2 oxygen, 2, 4, 5, 4, hold on, I did that wrong. That would be 2 plus 2 is 4, and 2 times 2 is 4. So 4 hydrogen, 2 chlorine, it's balanced. So we know 1 mole of this reacts with 2 moles of this. So the ratio is 1 to 2. We're trying to find the concentration of HCl, and the concentration we will use is molarity. Molarity is moles per liter solution. So how many moles? So we're adding 27.4 milliliters of 0.0154 molar. How many moles do we have of barium hydroxide? So the molarity that we're using is 0.0154 moles per 1 liter. Our 1 liter is equivalent to 1,000 milliliters. And I want to get just moles, so what will I multiply? .4 milliliters. That cancels out the milliliters, leaving me with just moles. So in our solution, or in our mixture, we have 0.42196 moles of barium hydroxide. I made a mistake. I forgot to divide by 1,000. I was assuming that was still 1. 0.0154 times 27.4 divided by 1,000. That gives us, I just moved the places over. That gives us 0.0004296 moles. Or 4.2196 times 10 to the negative 4 moles of barium hydroxide. So this is how many moles I have, and what's the ratio I'm adding. So I neutralize when I added this amount of HCl, my solution. So, but I know it neutralizes whenever I have a 1 to 2 ratio. So how many moles of HCl must I have in 20 milliliters of HCl? It's that simple. So imagine this number was 1 mole. then I know this 20 milliliters would have to have contained 2 moles, because I know twice the number of moles of this one is how much it is needed to neutralize it. So I know this 20 millimeter solution has to contain twice the moles of barium hydroxide to neutralize it. So that means in 20 milliliters, so that means we have, let me just, so we have 4.2196 times 10 to the negative 4 moles of barium hydroxide. And we know that we have twice as many moles to neutralize it, so we just multiply that by 2. Of HCl. And what is molarity? Molarity is moles per liter. And we know that this number of moles has to be in the 20 milliliter solution. So to figure out the concentration, it's 8.432 times 10 to the negative 4 moles per 20 milliliters. And I need to convert this into liters. So 1,000 milliliters is equal to 1 liter. So the concentration of the acid has to be 0.042196 molar. Make sense? So basically all we did is we started out with a container that had 27.4 milliliters of a known concentration. We knew that this was precisely 0.0154 molar solution of barium hydroxide. And we continually added acid until we added 20 millimeters of our unknown HCl. At which point we magically know it neutralizes. I'll go into how we magically know in a little bit. But we know after adding this amount, it's neutralized. There is no more HCl and there's no more barium hydroxide. To a certain degree. Chances are you aren't very precise in adding one atom so that it's on the atomic level matched up, and then there's other issues. But you know you're very close. You know that within limits to your ability to measure 20.0 milliliters and 27.4 milliliters, it's within 1/10 of a millimeter of being perfectly neutralized. And from this, you can calculate exactly the strength of an HCl. As long as you know precisely this volume and that strength and this volume right here, you can know exactly how strong that acid was. And you do that because you figured out that the equation is 2 moles of HCl has to react, or 2 molecules of HCl react with over 1 molecule of barium hydroxide. So if you have 1 mole of this, you know what you added had to have been 2 moles of this. We knew that it was 0.000414296 moles of this. So we know we had double the amount of moles in that solution that we added to 20 milliliters. So we had 0.0084392 moles of this. We knew the volume we added. So we know moles. It has to be this because we calculated how many moles this is. From molarity and milliliters, you can extract the number of moles in the solution. And since we know the volume and the moles, we can calculate the molarity of this. So how do we magically know when it's neutralized? If you just mix them together. So HCl is a clear liquid. Barium hydroxide is a clear liquid. It does produce barium chloride, which is a white powder that would fall to the bottom. But so there's not really any color changing. Let me look at the spelling of this thing. Phenolphthalein. One of my favorite chemicals. It's both loved and hated. Phenolphthalein. Is a chemical that is bright pink in basic solutions. Between pH 8.3 to 10.0. We'll go into what pH means later. pH is a logarithmic measure of the concentration of H plus, I'll put in quotation marks, H3O plus, ions in a solution. Its equation is, I believe, the pH is equal to the negative log of, and this symbol, these square brackets means concentration of H3O plus. Basically, only thing you need to know about acid for this context is our pH, I mean. Water has a pH of 7. Acids, so very, very strong acids, are around 1. Very strong bases are around 14. If you go, so have y'all worked with logarithms before? So if I have a log value, so these are log values, and I go from 10 to 11, how much have I increased the value? So these are log values. How much has the value changed? If I went from 8 to 12, what's the difference? How much has the concentration gone up? Or how much has the value actually gone up? If these values were logarithmic. For every 1 you increase, you change by 10x. So going from 10 to 11, 11 is 10 times bigger than 10. So what would this be? This would be 10,000 times bigger. Going from an 8 to a 12 means the concentration is 10,000 times as much. So these are logarithmic values. So the difference between a 7 and an 8, not that much. But the difference between an 8 and a 10, that's 100 times bigger. Let's see if I can get a plot. I don't think we have enough to actually go through and plot this or time. But it's... This is a good article that explains it. I'll link it with the video. So if you're mixing a strong acid with a strong base, phenolphthalein is very bright purple in this range, or very bright pink. So if you have a strong base that's between 8 and 10, then your solution will be extremely bright pink. And this is the volume of acid being added to your solution. You can see that there's, when it's neutralized is when there's only water, when there's no more acid or base. So a solution that has been neutralized is at 7. So if you're slowly adding acid to your solution, and you see it turn bright pink, and you immediately add the tiniest drop later, and it disappears, then you know you've passed the neutralization point. Does that make sense? So even though phenolphthalein is between 8.3 and 10, it can capture the neutralization point. The reason why I say this is a beloved and hated chemical, I remember in lab, so the thing is, you're going to put the tiniest drop into it, and then you're going to swirl it around. What you're trying to do is get it to be ever so slightly pink. So you're going to sit there, you put a drop in it, and you mix your basic solution with acid being onto it. It's super bright pink. And then you put the tiniest drop into it, and you screw it up, and it just immediately clears. And you've added way too much. So at that point, you don't know how much you exactly added, so you need to restart. Throw your solution away and try again. And it's really, and another thing that's, so what happens when you try to pour a drop into something? What can occasionally happen? So you drop a drop into it, and some little tiny bits cling to the side. And what happens when you swirl a solution? Occasionally you can swirl upward and collect a drop, and your solution instantly clears up, and you don't know why. Restart over. So it's very frustrating to get accurate. I did manage in my class to get a perfect solution. I do not remember if it was my first time, but I know the professor was impressed on how clear it was. Because it had the ever so slightly pink, or better yet, whenever you swirl it up, if you have it right at the perfect thing, you can separate the acid and base slightly and get the top portion being slightly pink. Basically, you can swirl it up and cause it to change colors. If it's right at the equivalence point, whenever you shake it up, you might see it turn back pink temporarily. And whenever you set it back down, it'll settle out and no longer be pink. That tells you you're at the equivalence point. It would actually... So, let me go back. On this one, I was saying it mildly wrong. So on this one, this is the case. This is the case for whenever it's a strong acid and strong base. So you're trying to get it. Again, you're testing for 7. But if you use a strong acid and a weak base, you'll notice that it stays pink for a long time. And the moment you're trying to measure is right here. Oh, that might not be it. This one. Weak acid versus strong base. You want it to be sitting there right at pink. So if you do a weak acid and a very strong base, it's going to be colorless, 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 colorless. And then right here, whenever you add the most tiniest little volume, see the difference of this volume versus that volume, there's a single point in which the solution stays pink, and that's the equivalence point that tells you have a 1-to-1 ratio of strong acid to strong base. Or you've neutralized it. Because I think phenolphthalein is slightly acidic too, and you have to account for that or something. I forget exactly what the difference between neutralization and equivalence point is. Right now, we're going to assume we can just magically know it's neutralized, in which case the pH will be 7. There is a difference, but basically you're trying to capture, and this volume can be ultra, like a speck of a speck of a speck of a drop, to get it to land right there. But if you know right here it's clear, you put a drop into it, it flashes pink, and then it's right over here, you can basically assume guesstimating it, but you're not very precise. This one would be terrible. You wouldn't be able to use phenolphthalein. There is methyl orange, another one. I never used that one. I've only ever used phenolphthalein. You're doing a weak acid with, let's see. You ever heard of a litmus paper? I assume litmus is ever put chlorine in a pool? And you have little things you go measure. Yes, that's litmus paper, and why I put litmus tape. That's another chemical that's color is sensitive to acid conditions. This. It's not very precise, and it can be used precisely. You put it in acid, and it changes color. I think it's red for acid. Something right here. So that's a quick way of comparing. You want to use the universal. So you basically put it in the solution. The paper is going to change color based off of what it is. And there you can roughly get an estimate of how much acidic it is. It's not entirely... You can't be that precise with it. You can get precise enough to do measurements and stuff, but for theoretical... Let's do another problem. You have a half molar solution of sulfuric acid. And let's say we have 100 milliliters of it. How many milliliters of 0.25 molar sodium hydroxide is needed to neutralize it? Mm-hmm. So, what would the equation be? Mm-mm. Binary HS would be hydrosulfuric acid. Hydro means binary. Without the hydro and the ick, tells you it's an 8. So it's sulfur with sulfate. What is sulfate? So it's a hydrogen, or it's a H plus with sulfate. So what is sulfate? So acid tells you it's H plus. What would sulfite be? So what's our 8 roles? SO4. So 8 always refers to O3, except for sulfur and phosphorus that have O4. And then what would your charge be? So what group number is sulfur in? What? It's in 6, so I give it a +6. Oxygen, we always have the oxidation number of -2. And the sum of oxidation numbers is the charge of the ion. So what is 6? Well, 4 times -2 is -8. So 2 negative. So what's the formula? Oh, what is sulfuric acid? What's the formula for it?
Oh, shouldn't it be 2?
No, it should be H2SO4. You need 2 H plus to counteract the 2 negative. Then we'll add to it NaOH. Mixing a base. This is a base. A base has OH. A base has hydroxide, while an acid has H plus. H plus and OH always gives you water. What would the other chemical be? Hmm? Speak up. So this is double displacement. So the OH and the H are going to combine to make water. That means so this is going to come over here. That means this must come over to this one. So it's going to have some combination of Na and SO4. But what should be the correct subscripts?
one H on the right. I need another, would it be?
I'm still talking about this. What's the correct formula for that? Yes, you need 2 sodium to counteract the 2 negative charge here. Sodium is Na+. So you have 1 plus charge and 2 negative charges, so you need 2 of these. Now we worry about balancing. Once we have the formulas all correct. So hydrogen, we got 3 on the left, 2 on the right. I wouldn't start there. Sulfur, we got 1, 1. Oxygen, we have 5. And we have 5. It looks like the only choice we have is to start with the hydrogen. So put a 3 here, 2 here. So that gives me 4, 5 hydrogen. Right? And that gives me 6 hydrogen over here. It's not the right choice. So again, to balance it, we know that we have, wherever this coefficient, I'll call it A. I'll call this coefficient B. And this coefficient C, this coefficient D. So for hydrogen, I know I have 2 times wherever A is, plus 1 times wherever B is, and that tells me how many hydrogen I have on the left. Here I have whatever C, so it'd be 2 times C, gives me all the hydrogen. For the sulfur, I know that wherever A is, it gives me all the sulfur, and whatever D is, so I know A is equal to D. For the oxygen, I have 4 times A plus whatever B is, gives me, so if A and B are 1, that's 5. And over here, that would have to equal wherever so C is, and 4 times whatever D is. And then sodium be whatever B is, and that would have to equal 2 times whatever D is. So I know that D is going to be half of B, or B is twice the number of D. So you can already guess, maybe you double this. So let's plug in and say B is 2. Maybe that's the best way of looking at it. So I know I need twice as much here, so I give 2 over here. That would increase this to 6, and that would increase this to 4. And then we can double the water here. So I put 4, and I put 6 here. Actually, that's the best way of doing it. Right? So the overall equation is H2SO4 plus 2NaOH is equal to 2H2O plus Na2SO4. So we're in the same situation. We need twice the number of molecules of this so we need 2 molecules of this for every 1 molecule of that. Or we need twice the number of moles of this as that. So how many moles of sulfuric acid do we have? Well, we know it's 0.5 moles per 1 liter. We need to convert that into milliliters because we're given 100 milliliters. So there are 1 liter per 1,000 milliliters. And we're given that we have a 100 milliliter solution. So liters cancel out. Milliliters divided by milliliters cancel out, giving us just moles. So we have 0.05 moles of H2SO4. And we know we need 0.1 moles of NaOH. But the question is asking how many milliliters. So we take the molarity of our NaOH. It's 0.25 moles NaOH per 1 liter. So we're gonna. We know we need 0.1 moles. Time. We start with 0.1 moles and we multiply it by this. And that's how you get your answer. And convert into milliliters. And that's it. This is your answer. 400 milliliters.